Next is Samantha Norris, who's joining us also from Cornell, and she's got some really cool stuff to tell us about tiny robots. So I'll hand it over to you, Sam. Thanks so much.
Okay, thank you. Can you all hear me and see my screen?
Yep.
Okay. So first of all, I actually did not know that fact about the solar panels, so it's a tricky one. And my robots are also not as cute as Michael's, but I think that's hard to beat. So I'm actually going to be talking, you guys have heard a little bit about robots so far today. I'm going to be talking about how to make them really, really tiny. So I am actually a grad student in the physics department here at Cornell. And in case you haven't figured it out, this is actually not a real image that you see on the title screen. This is actually a still image from kind of an older movie made in the 60s called Fantastic Voyage. But it's sort of, we're using it as our inspiration. It's basically about a bunch of guys that shrink down into a little submarine, and their little submarine travels around in the bloodstream and in the brain to try and help a scientist who is actually kind of sick. And so they're trying to make him healthy again. And that's sort of our inspiration, is making tiny little robots that are helpful. But first, let's think about robots for a little bit, right? You know, my personal favorite robot are these Mars rovers, right? This is the Spirit rover, and his entire job is to just kind of, you know, he wheels around and he takes data and analyzes it and then sends it back to Earth. And it's really pretty cool. But, you know, the obvious question is, you know, why do we need robots on Mars? And obviously humans haven't been there yet. You know, maybe we'll get there one day, but for now we haven't had luck yet. And so if humans can't go to Mars to study their own data, we need robots there. So what's another application where we could use robots to go to a place where humans can't go to study things and then send that information back to us? Well, what about, you know, really small things, right? Like what about, you know, inside your brain or in your blood vessel? So imagine if in a couple years you took a magnifying glass into your brain and you see these tiny little Mars rovers, like, you know, going around, swimming around, taking data and sending it back out. And they could tell you, you know, if something's wrong in your brain and you don't know it yet, or, you know, it could even deliver medication. Same thing in your blood vessel. Maybe it could tell you if you have a disease before you even show symptoms and send that data back out. And they're so small that they don't really affect anything. So, you know, that's not a big worry. It's a little bit terrifying to think about, I'll admit that, but it's actually, it can really be a good healthcare tool to, you know, provide medication to your body. So, you know, the obvious question is, how on earth do you make something that small, right? And, you know, how small are we talking? So let's go back to those examples of, you know, a brain cell, which is called a neuron, or maybe a red blood cell. It turns out those are about the same size, about 100 micrometers, give or take. And so let's say that our little robots, which are what my research group makes, we make those little robots that are about 100 micrometers in size. So we take those robots and we line them up one by one. It would take about 25,000 of them to make 1 inch. That's how small they are. They're so small you can't even see them. And so I'm going to show some robots that my group has made. And we put them on a penny just to show how small they are. And I don't know if you guys know this, I didn't know this, but you know, on the back of the penny, there's the Lincoln Memorial. But if you actually zoom into the Lincoln Memorial, there's Abraham Lincoln sitting there. And we put this little robot on his chest just to show how small it is. So that penny on the left, there's actually a tiny little robot there, but you can't see it. That's how small it is. And so I'm going to be talking a little bit about what these robots do, but for now, that's sort of the size scale that we're talking about. And just for another point of comparison, 100 micrometers is about the width of a human hair. So if you take a hair off the top of your head and you look at it, it's about 100 micrometers wide. It's really small, okay? So again, you know, how do you make something that small? Well, it turns out we're actually really good at making small things. I mean, you're watching this on a computer or a cell phone or a, you know, a TV or something. All those things, any electrical thing that you can think of has millions, if not billions of electrical components in it that are so small you can't even see them, like transistors or capacitors or resistors. We're really good at making small things. And so what our team does is we just take some of that technology and use it to make robots. But look, these are circuit boards, right? They're boards, they're flat. So the question is, how do we go from 2 dimensions to 3 dimensions? Well, maybe some of you guys have done this before with origami, right? Origami is the Japanese art of paper folding, and you can basically take a flat piece of paper and do a bunch of folds to it, mountain and valley folds to go both directions. And you end up, this is a swan. So you take this piece of paper, you fold it, and you end up with this 3-dimensional swan. And it turns out, one of the points of this entire talk is that you can just take big things and make them really small. The physics is essentially the same. And the same is true for origami. You can make tiny little panels. So this is glass. It's a couple materials, but glass is one of them. It's only about 20 atoms thick. And you can fold it, and this is the world's smallest origami bird that my coworker Barish made. And so again, it's about the size of a human hair, and the paper is only about 20 atoms thick. And you can just take origami and make it really small, it turns out. So how do these things work? I'm gonna give a brief little example here. To make something that's small that bends, you have to know that basically water has a bunch of positively charged atoms in it. It's like positively charged water, okay? And our little origami robots are made of 2 materials, one that loves these atoms and one that hates these atoms. And so if you just kind of wait long enough or you apply enough energy to it, eventually those atoms go into the material that loves them, and it gets bigger, it swells, and so it starts to bend. And so what happens is there's more of these positively charged water molecules in acid than there are in water. So if you take these 2 materials, you put them in water, they're flat. If you put them in acid, even like lemon juice or something like that, they start to bend. And so doing that, we can just make all kinds of shapes. And in here, the green material is glass in this example, and the pink material is a material called graphene. And you can make all kinds of origami shapes. So here in the chart on the left, in the right panel, you see basically us making paper models. And then on the left, you see the unfolded and then the folded version of the sort of tiny object. And again, all of these are significantly smaller than the width of a hair. They're all really tiny. So now we've talked a little bit about how you take the tools from circuit boards, which are flat, and you make them 3-dimensional to make a sort of 3-dimensional robot. But what do we actually want our robot to do? Like that's really important. So let's go back to our little Mars rover and see what he's up to, and see kind of figure out what we want our robot to do. So this Mars rover, he can move around, right? He has little wheels and he can tour the landscape. He can also sense the environment and take measurements of the atmosphere and the soil, and he can send that information back to us. So those are the 3 things that we're going to use as examples for what we want our tiny little robots to be able to do. And so let's think about those. So first of all, my personal favorite is making robots that move around. And it turns out at the micro scale, so when things are cell-sized, a lot of the science is the same as when things are big. And that's something I really want you guys, that's sort of the take-home message, is you can start to think about those things now. So first of all, one of the things that we've made, that my coworker Michael has made to make robots move around is called a flagellum. So this is actually a cell that I'm showing you an image of, or a movie of, and it has a flagellum out of its back end, and it just kind of waves that around, and that's how it moves. And it turns out you can actually make an artificial flagellum. And so this is basically using the same principle as what I was talking about with the origami, the same method of working, more or less, and making a little flagellum that waves. And these guys aren't swimming yet, but I think that's very soon. So the next way of moving around is, what about a rocket? Could you just make like a really tiny underwater rocket? And it turns out it's really hard to put rocket fuel on a tiny little robot, but you can make bubbles and eject them. So this is actually my project, and I love it. And I think these guys are cute, but not as cute as Michael's robots. So this is a bubble rocket, and just like Barrett said, each of these 7 little panels here are solar panels. They're solar cells, just like you would see, um, maybe on top of your house or out in a field. It basically takes light and converts it into energy. And so each of these little black lines here are wires. So they're all wired up and connected to these little electrodes here. And these electrodes are sort of hollow on the inside. So what happens is if you apply enough electricity in water, you make bubbles. And these electrodes are shaped so that they shoot the bubbles off in one direction. And so that's the principle behind these little bubble rockets. And if you have it floating, you can actually, so this is a bubble rocket, which I call them, swimming in water. And this is a real-time video. And so all of this is, these are about the same size as a red blood cell or a neuron, or about the width of a hair. So these guys are just swimming around, and we're in the process right now of making them steerable, but for now they just kind of go in whatever direction they please. So that's one technique of making something that moves around like that. So what's another sort of method that you can think of for robots? And maybe you guys have already seen talks like this. And the answer is making things that just sort of walk around. So one of my coworkers right now, while he's sort of social distancing and he's kind of in isolation, he's been making Lego robots to study different gaits of robots, meaning like how you should have the legs move and with what timing to be able to move the fastest. So he's just been putting Legos together and programming them to be able to walk. With hopes that we can make these, tiny little robots. And we've actually made something very similar, which is this tiny little robot that can also sort of move around and walk. And so this is also in water, I believe, and it's just walking around on the surface, on the bottom of the dish. And he has little legs that, again, using the same technology that we use to make the little origami things. You're applying electricity. Each of these little rectangles here is a solar panel, and the white spot here are laser spots. So you're applying electricity. You're shining light on the solar panels, which is making electricity, which is causing these legs to bend. And so it's walking that way, which is really interesting. So those are 3 techniques to sort of move around at really small scales. And again, a lot of this can be thought about when things are big, and then just making them tiny is the challenge. So we talked a little bit about moving around, but what about being able to sense their environment, right? That's, if we had a robot that just kind of walked around your body, that's not really helpful. That's not really helping anyone, right? You want it to be able to take data and to send that information off to us to be able to study. So I'm going to talk about a couple different robots here, and these first 2 are actually not things that our group has done, but I think they're still really interesting. So first of all is glucose sensors. So if any of you are diabetic, or you know someone who is diabetic, you constantly want to measure your glucose, because if it goes too high or too low, you can have some serious, you can get really sick. And so these little sensors go in your body, and they're constantly measuring glucose and sending that information back out to be studied. It can even be read with a smartphone or something like that. And also neural sensors. So if you guys remember, these cells in the brain are called neurons, and neural sensors, they're implanted in your brain, and they can measure your brain activity and send that information back out. So it can tell you whether you have some brain disease that you don't know about yet. And so that's really helpful. But 2 sensors that our group has made, one is being able to sense magnetic field. So these are a bunch of tiny little robots, or tiny little magnets, just like a refrigerator magnet, just like a big magnet that you would think about, but just shrunk down, really small. And they're being actuated by an external magnetic field. And so being able to sense magnetic field is something that we can do right now. But also tiny little thermometers. Right? So this is a thermometer that we actually implanted in a mouse's brain. And it's pretty wild. This mouse was like, it didn't die or anything. It's too small to be able to be felt by the mouse. And so it just continued living on its happy little mousy life after we implanted this. But what you can see in this picture is actually the yellow is the device that we put in. And again, it's about the size of a cell. And then the red that you see surrounding it are actually the little blood vessels in the brain of the mouse. And so the question is, we put this thing in the brain and we can power it with solar cells, that's all fine and good, but how do you get that information back out? So the last thing that we need to talk about is, how do you send that information back out? Well, it turns out there are a lot of ways to do it, but one of them is with light. So this is a tiny little LED that we've made, and it's about 1/10 of the width of a hair. So it's about, 8 or 10 micrometers wide. And you can see it gets really bright, actually. And so we can communicate that light back out. And this is basically the same thing as like an LED Christmas lights. It's same thing. You apply electricity to it, and you get that light. You get that light back out. And a lot of things communicate with light. So for instance, like TV remotes, I have one here. If TV remotes actually communicate with light, but it's a wavelength of light that you can't see. So if you press a button, you can't see the light coming out, but actually cameras can sort of detect this. So if I press a button, my webcam can actually detect that I'm pressing a button. And so TV remotes are just an example of something else that communicates with light. You can also communicate with, radio waves or sound waves, all kinds of stuff. And a lot of robots, tiny robots are made that utilize those things to be able to communicate. And so again, just looking around your world and seeing, what the ways that things communicate, and then thinking about how to shrink those things down is really useful. So that's all fine and good, but what's the point? I've shown you robots that can move around, they can sense their environment, and they can transmit that data back to us. But they're all using tiny versions of things that already exist. So things like origami that maybe you guys have played with, or solar cells that you guys might be familiar with. LEDs like Christmas lights or TV screens, things like that, and magnets. All of those things are things that you guys are familiar with. And the point is, you don't have to be like a fancy scientist to start thinking about what kind of tiny robots can be made using those things. You can start, like, the hardest part, I would say, of all of this is actually looking around your world and thinking about what would be useful as a tiny robot. And what do you want in your ideal tiny robot? Because this field is never finished, right? You will never have the perfect tiny robot. You can always improve on it. And I really want to encourage you guys. I think that this is a field that is really starting to take off. I think that in the next century or so, even, or the next couple decades, tiny robots are really going to be something that we're going to need a lot of people to start thinking about and starting to make. And so as your guys are starting to enter high school and college and starting to think about what you want to do afterwards, I really encourage you to sort of always be aware that this is something that exists, and to start thinking about it. So thank you so much for coming to my talk, and I will be happy to take any questions.
All right, awesome. Samantha, that was great. Thank you so much. So we have a bunch of questions of people that are very curious, and I'll try to combine them as much as possible and we can answer them. So the first one, so Amelie and Zaraha asked a similar question. Basically, like, when you make these bubble rockets, or if you make any of these types of tiny little robots, what happens if you try to put them in the human body? Does your body try to destroy them? Like, is there going to be any kind of adverse reactions and negative reactions? And yeah, so kind of that.
So that's a really good question. And one thing I didn't point out is that those bubble rockets are actually made of, like, they're coated in glass. Everything on the outside is actually glass, and glass is it's called biocompatible. It's very compatible with the human body. And so the way that we test that is we actually take, like, these devices. We haven't done that with these yet, but there have been other people who have done that with glass, and they try to grow cells on top of them to see if those cells don't like that device. And we chose glass because cells don't really seem to notice that it's there, and so it's very perfect to be put in the human body.
Cool. Okay, great. So Iwan is asking, how can you store a lot of data in something that's so small, like the width of a hair? It's a great question.
That's a really great question. It's actually a really hard one too. So for these robots, we're not storing any data. We're just like, constantly taking data and constantly sending it back out. But if you think about computers, right, like your hard drive, how does your hard drive work? And it turns out it's a bunch of magnets, and you have this little magnetic like right head that goes across like a string of magnets, and it will sort of flip the magnetization. And those magnets are basically stored with that sort of magnetization until something comes across to change it again. And so magnets, that's actually the reason why we're starting to think about magnets, is because it's a really easy way to store information at a really small scale.
Yeah, it's cool. Okay, more questions.
Yeah, good.
So this one was by 3 people. Alora, Lila, and Mary all want to know, you did kind of talk about this. Sorry if I'm breaking up. It's telling me my internet connection's unstable.
No, you're fine.
I want to know how you actually make them so small. Like what kind of tools, I guess, you use to do that.
Yeah, so that's a really good question. So Cornell actually has, it's called a nanofabrication facility. And all that means is basically we can use the same tools as grad students that people use to make circuits. And it's actually can be thought of pretty simply. So one of the things that we use, as its long name, is called photolithography. And basically the story is you can spin, or you can, deposit a really thin film of something, and that something reacts really strongly with light. So what you do is you can basically shine light at very specific locations and do things, and it will basically dissolve that material. And then from there you can do all sorts of chemistry to remove parts of your chip and your sample and things like that. All that to say, it's basically all light activated. You're shining light onto materials to remove them and to add more materials and things like that.
Okay.
Sorry, that's not so super clear.
I think it was great. Okay, so Quinn is asking, since the robots are so small, how do you find them in the water? There's a similar question to this, but yeah, like basically, how do you take these videos? How do you see them?
Yeah, that's a really good question because it's sometimes really hard. Sometimes a lot of my day is spent moving around a petri dish under a microscope trying to find these little devices. But the answer actually is that we could make them millions at a time, because we just have like a sample that's maybe this big, and it's a square piece, and on there are hundreds of thousands of devices. And so if we just put all of those in water, they can all float away at the same time. And you look for long enough, you'll eventually find a couple.
I guess with 1 million, you would hope so.
Yeah, right. Yeah.
Okay, so Brooke is asking, what strategies can you use to independently control each bubble rocket? Is there a way to do that? You just talked about 1 million, so what about one?
Yeah, so that's a really good question. And basically we can make them however we want. So for instance, if they're light powered, and if you just use a laser, lasers have a pretty small spot size, so you can control them independently. We're actually working on making more complicated bubble rockets right now that have multiple solar cells, and that can be sort of steered by controlling which rockets you use at one time. But for now, we just kind of use like a really small laser spot that can only activate one at a time.
Cool, very cool. See. There's definitely some more in here. I'm just
That's great. I love talking about this, so this is great.
No, it's great for me here. So I do biology. So
oh yeah, nice.
Very different. Though I do look in a microscope and try to see small things too.
It's great. Yeah, it's hard sometimes.
Okay. All right. So Audrey's asking, so if using light to transmit info once inside the body, how is the info transmitted outside the body? So how do you get that information back?
So actually, it turns out that LEDs work pretty well. So one way that you can actually see this is, I don't have a laser pointer with me right now, but the transmission of light through the body depends a lot on the color. And so if you have like a red laser pointer and you hold it up to your thumb, you'll actually be able to see the red on the other side. If you do that with a green laser pointer, you won't be able to see the green. And so that's a good little example. But it turns out that red light especially is really good for being able to be transported out the body. So if you have a solar panel that, is excited by green light, which is what we use, and an LED that emits red light, it actually works really well for transmitting out of the body.
That's very cool. Okay. Sorry, I'm waiting on some more. Okay, there's a couple questions that ask sort of about like you yourself, like when did you get into robots and like what age were you? I mean, Michael's answer was very young, so is it the same for you?
So actually for me, I had sort of the opposite experience, which is that all of my high school and college, I wanted to do computer programming. And so my undergrad was actually in computer physics. So I never looked in a microscope as a college student, um, which, which honestly, my pitch to my like current grad school advisor was, I don't know anything about what you do, but I find it really cool. And so, I think a lot of that is actually a benefit for me, which is that I don't know what's possible and what's not. I'm just not as well versed in all of that. And so I have a lot of ideas that, maybe people haven't thought about. And I think that's true for everyone.
All right, that's great. I think we are just about good for time. Thank you so much. You did a
Thank
great job
you.
answering all those
Great questions, guys.
Awesome. Yeah, there's so many great questions.
All right, see you.
That was so awesome, Sam. Thank you for that presentation.